Here is something that really gets me. People look up at the night sky and they see all those stars, billions of them, and they think, well, surely somewhere out there there is somebody looking back. And that is a perfectly reasonable thought. The universe is enormous. The numbers are staggering. There is something like 200 billion stars in our galaxy alone, and there are maybe 2 trillion galaxies in the observable universe. So when you multiply those numbers together, you get something so big it stops meaning anything to your intuition. You just stare at it like a child staring at the ocean for the first time. So people conclude, and quite sensibly, that given all those stars and all those planets, life must have arisen elsewhere. Maybe intelligence too. And then the next step people take, and this is where the thinking quietly breaks down, is they assume that if intelligence exists out there, it can come here. That is the assumption I want to examine today. Not the question of whether life exists elsewhere, which is genuinely open and fascinating. I want to look at the physics of the travel itself, because the physics is brutal. And most people, even smart people, have not really sat down and thought through what it actually costs to move an object from one star to another. Let us start with the nearest star to our sun. That is Proxima Centauri, sitting about 4.2 light years away. Now a light year sounds like a unit of time, but it is actually a distance. It is how far light travels in 1 year, moving at roughly 300,000 kilometers per second. That is the fastest anything in the universe can move. And we know that not from convenience or lack of imagination, but from the deep structure of space-time itself. So 4.2 light years means that even light, the absolute speed limit of the cosmos, takes 4 years and a couple of months to make that trip. Nothing goes faster. Now you might say, all right, for years is not so bad. Pack some sandwiches and go. But that framing misses the real problem entirely, because the question is not just how long the trip takes. The question is, what does it take to accelerate something to a meaningful fraction of the speed of light, to keep it going, and then to slow it back down at the other end so it does not just shoot past the destination planet like a bullet through fog. Think about energy. When you push something and make it go faster, you give it kinetic energy. In ordinary, everyday life, the formula for kinetic energy is 1/2 times mass times velocity squared. That is the formula you learn in school, and it works perfectly well when you're throwing baseballs or driving cars. But as you approach the speed of light, something strange happens. That formula stops working. You need the full relativistic expression, which tells you that the energy required to accelerate a mass does not grow merely as the square of velocity. It grows without bound. The closer you get to the speed of light, the more energy you have to pour in, and it keeps demanding more and more for smaller and smaller gains in speed. You can never actually reach the speed of light with a massive object. You can get close, but close costs an extraordinary amount. Let me give you some numbers that will make this concrete. Suppose you want to send a modest spacecraft, nothing fancy, maybe the size of a small car, say about 1,000 kilograms, and you want to accelerate it to just 10% of the speed of light. That is still 30,000 kilometers per second, extraordinarily fast. The kinetic energy you need to give that object is roughly 4.5 times 10 to the power of 18 joules. Now, the entire world right now produces and consumes energy at a rate of about 5 times 10 to the power of 20 joules per year. So to push that one small spacecraft to 10% of light speed, you need energy equivalent to roughly 1% of all the energy humanity produces in an entire year. And that is just for the acceleration phase. You have to do it again at the other end to slow down. So you need twice that at minimum. And this is just 10% of light speed, which still means a 42-year trip to Proxima Centauri. If you want to make the journey in, say, 10 years instead of 40, you need to go faster, and the energy requirements jump dramatically because of that squared relationship. Go to 20% of light speed, and the energy required roughly quadruples. Go to 50%, and the numbers get almost laughable. We are talking about energy outputs comparable to entire civilizations running for years just to move one ship. But it gets more interesting and more sobering. I have been talking about getting energy into the ship to push it. Where does that energy come from, and how do you carry it? Because here is a second layer of the problem, and this one is called the rocket equation, named after a fellow named Tsiolkovsky who worked out the mathematics about 100 years ago. The basic idea is simple. A rocket works by throwing stuff out the back. The faster you throw stuff out the back, the more efficiently you move forward. But here is the catch. That fuel you are carrying has mass, and that mass has to be accelerated along with the rest of the ship. So you need fuel to carry the fuel, and you need fuel for that fuel too. The mass of propellant required grows exponentially with the desired change in velocity. This is not a problem of engineering cleverness that you can simply solve by building a better rocket. It is a problem that is baked into the mathematics of momentum. To get a payload to a meaningful fraction of light speed using a conventional reaction drive, the ratio of fuel mass to payload mass becomes astronomical. You would need essentially a mountain of propellant for every kilogram of useful cargo. The ship would have to be almost entirely fuel, which means less room for everything you actually wanted to bring. People then ask about antimatter. Antimatter is the most energetically dense fuel imaginable. When matter and antimatter meet, they annihilate completely and release energy with 100% efficiency, compared to about 1% for chemical rockets and maybe a few percent for the best nuclear fission engines. So antimatter sounds like the answer. And in principle, it does help enormously. An antimatter rocket could theoretically achieve very high exhaust velocities and make interstellar travel far more feasible in terms of energy density. But the problem is making antimatter. We know how to produce it in particle accelerators. We do it all the time. The problem is that making 1 gram of antimatter, just 1 gram, would require something on the order of 25 million billion joules of energy input. And it would take our current particle accelerator technology longer than the current age of the universe to produce a kilogram of it. So antimatter is real. The physics is sound. But the production rate compared to what you would need is so far apart they might as well be in different conversations. Now here is something even more fundamental that most people skip right past. Even if we solve the energy problem somehow, even if some civilization has a power source we cannot currently imagine, there is still the problem of hitting things. Space looks empty when you stare up at a clear night sky, but it is not truly empty. Between the stars, there is a thin scattering of gas and dust and the occasional larger particle. This is called the interstellar medium. At low speeds, this is completely irrelevant. But when you are traveling at 20 or 30% of the speed of light, even a single hydrogen atom, which is essentially just a proton, hits the front of your spacecraft like a particle accelerator beam. At those speeds, the interstellar medium becomes a radiation bath. A spacecraft would need extraordinary shielding at the front, and that shielding has mass. And mass means more energy required. The problem compounds itself at every turn. Then there is the time issue, and this is where it gets philosophically interesting. Relativity tells us that time itself slows down for moving objects. At very high fractions of the speed of light, the crew aboard the ship would age more slowly than people back home. This sounds wonderful until you think about what it means in practice. If a civilization sends a probe or a crew to a star 40 light years away and they travel at 90% of light speed, the crew might experience only about 20 years of travel time due to time dilation. But back home, roughly 45 years have passed. The society that built the ship has changed. The people who wave goodbye are elderly or gone. The mission parameters might be obsolete. Communication is essentially impossible in any real-time sense, because even signals traveling at light speed take 40 years to make the round trip. So what you have is this picture. Interstellar travel is not merely difficult the way climbing a very tall mountain is difficult. It is difficult in a way that seems to come from the deepest structure of how the universe is built. The speed limit is not a technological barrier. It is a feature of space-time geometry. The energy costs are not a matter of lacking clever engineering. They follow directly from the mathematics of relativity and momentum. The communication delays are not a solvable communications problem. They are a consequence of the finite speed at which any signal can propagate. Now, some people at this point will bring up wormholes. The idea that you could punch a tunnel through space-time and emerge elsewhere without having to traverse the distance in between. This is a genuine solution to the equations of general relativity. The mathematics does allow for such structures in principle, but there are several enormous problems. First, creating a wormhole that a macroscopic object could pass through would require something called exotic matter, which is matter with negative energy density. We have never observed this in any quantity that would be useful. We have hints that something like it might exist in quantum field theory at very small scales, but nothing remotely close to what you would need to hold open a wormhole large enough to matter. Second, There are serious theoretical arguments suggesting that even if you could create a traversable wormhole, the moment you tried to use it for faster than light travel, it would become unstable and collapse, possibly violently. The physics keeps putting up barriers. So here's where I end up when I actually sit down and work through the numbers. The fermiparadox, which asks why we have not seen any sign of alien civilizations despite the universe being so large and so old, might have a very boring answer. Not boring in the sense of uninteresting, but boring in the sense of straightforward. The universe is enormous, yes, but the distances between things in the universe are also enormous in a way that matches and possibly exceeds the ability of any physical object to traverse them within any practical time frame. A civilization could exist around a star 20 light years away. They could be broadcasting signals and building incredible structures and philosophizing about the nature of reality, and we might simply never know. Not because they are hiding, not because they are afraid, but because the light from what they are doing takes 20 years to reach us, and the idea of physically traveling to say hello runs into physics that appears to be impassable at anything close to civilization-ally relevant speeds. This is what I find both humbling and deeply interesting about the question. People frame the absence of alien visitors as a mystery, as if something strange is being hidden. But when you look at the energy budgets, the velocity constraints, the fuel mass requirements, the radiation environment at relativistic speeds, and the communication time delays, the more natural conclusion starts to look like this. Maybe the cosmos is full of life, and maybe intelligence has arisen many times over, and maybe those intelligences are doing extraordinary things on their home planets and in their home systems. And maybe the distance between them is simply the answer. Not a conspiracy, not a barrier built by someone, just geometry, just physics, just the way space is put together. The universe gave us all the ingredients for life to appear and for minds to emerge and to look around and ask questions. It did not, however, make it easy to meet your neighbors. And there is something almost elegant about that, if you sit with it long enough. The same equations that allow stars to burn and planets to form and carbon to be cooked up in supernova explosions, those same equations impose a speed limit that makes the distances between those stars almost impossibly hard to cross. It is the same physics, doing two different things at once, creating the conditions for life and almost guaranteeing that each pocket of life remains profoundly alone in any practical sense. That is not a comfortable thought necessarily, but it is, I think, the honest one.